We will complete we'll start from what Mr. Eric ended, and we'll just see the technical part. When you have the ECG, okay, paper to produce this paper, you need to apply the leads. Then you need to read this paper. So how to do that? So first, we'll see the lead placement. So it's important to put the lead placement in the right position, because as Mr. Eric explained, it's electricity. Electricity goes in directions. Okay? So you want to catch electricity that's coming from the heart. And all organs produce electricity. Okay? All organs produce electricity. So you want the electricity coming from the heart, so you want to put it in the right position. So this is the right position. Make it first starting by lead 1 and lead 2. They said V1 or V2. V is for vector. Okay? V is for vector. So for vector 1 and vector 2, you have to put them in a fourth intercostal space at the side of the sternum, right and left. Okay? So now we are doing the left-sided ECG. Left side ECG, okay? Sometimes you may be asked to do right side ECG. So left side, this is the normal one, this way. If you do the right side, you will do the other 3, 4, 5, 6 leads on the other side, okay? Same, start from opposite. But anyway, you start from the right side of the patient, put lead 1, and put the lead 2 on the left side of the sternum. Then you will put lead 4 at the 5th intercostal space at mid-axillary line. Mid-clavicular line. So where is the mid-clavicular line? You see the clavicle? There is a bony prominence here, starting from here to the shoulder. Okay? And divide this in the middle. This is your mid-clavicular line. Intersecting with the 5th intercostal space, this is where you put the lead 4. Now why I jump to lead 4? Because easily you can put lead 3 between lead 2 and lead 4. Okay? Put lead 3 between lead 2 and lead 4 in the middle. Okay? Then if you have a small patient, try not to put the leads overlap. Okay? Try to minimize the overlap between the leads so they will not interfere with each other in the leading. Then you will have lead 5 and 6. So we will go to jump to lead 6. Put it in the 5th intercostal space in mid-axillary line. So where is the mid-axillary line? Visually between the beginning of the chest and the back. Okay? In between, this is the axilla. Divide the axilla in the mid-axillary line. Put the lead 6 intersecting with the 5th intercostal space. Then lead 5 between 6 and 4. Okay? This is for the chest leads. What about the limb leads? Put the limb leads at the anywhere in the limb. Okay? But put it in the equal position. Sometimes if the patient have amputation. Okay? If the patient have amputation, you put it at the limb. At the limb, preferably not on muscle. Put it on probably you put it here, right? Okay? Because if the patient have muscle contraction, it will pick this up. If you put it on the muscle, it will pick it up. So put it on bony prominence, so less activity. So it will catch electricity pure coming from the heart. Okay? If the patient have burn, if they have a pacemaker, try avoid this area. Okay? If they have a pacemaker, if they have an implanted device, if they have fresh wounds, try to avoid these areas. Okay? So it will give you, maybe it will not give a reading, or it may give artifact, may cause pain for the patient. If the patient have nicotine patch, if the patient have nitroglycerin patch, fentanyl patch, don't put on top of anything. And when you do placement of the lead, you need to prep the skin. So how to prep the skin? Who tell me? Huh? How to prep the skin? If there is hair, remove. What else? Huh? Yeah, dry. What else? Also, if it's dirty, clean. Cleaning. Yeah. Cleaning. And also avoid interference from other electrical devices. But we're talking now about prepping the skin. So cleaning the skin, if there is extra hair interfere with the connection of the lead, remove. If it does not interfere with the connection of the lead, it's okay, you still use it. Like if the patient have long hair and it's thick, it will interfere with the connection of the leads, you have to remove. Okay? So this is the sternum, side of the sternum for lead 1 and lead 2. Lead 4, mid-clavicular line, and between them, between 2 and 4 is lead 3, and lead 5 and lead 6. So here about the limb leads, the important one is LL, left leg, and left arm and right arm. But the right leg, it does not produce part of the ECG, but is very important for making your ECG without artifact. Making your ECG without artifact. Lead right leg, place in the right leg, is ground lead. Ground lead. Electricity is normally there is artifacts in any electricity. So to discharge this artifact and you have the pure ECG, we place the right leg lead. So if you see ECG not clear, probably your right leg lead is not attached properly, or the lead is broken, or the wires are broken, etc. But if you are disconnected from left leg, you will not see ECG. Okay, also others. If you disconnected from lead 1, 2, 3, you will not see the lead 1 or 2 or 3. But lead left leg also affect other leads. Again, this is a placement for those leads. Now, if I have a problem with my ECG tracing, how can I solve those problems? So after skin prepping, make it a standard. You remove 50% of the causes of artifact in your ECG. Okay? No need to write again, print again, try again. If you prepare the skin properly, you remove 50% of the problems. So what are the other 50%? The remaining of the machine. So patient and the machine. And now you prepare the skin. Now the patient. Patient can be moving. Patient can be having shivers, right? So this makes the muscle move. Okay, and they produce electricity also. So this interferes with your ECG. So chest muscles can move, can shiver, arm muscles, all of this will cause electricity and it will interfere with your ECG. So you let the patient be calm if he can listen to you, and also don't do it, for example, after morning bath. If you expose the patient after morning bath, he may have shivers. Okay, better do it before the bath. Okay, you may need to clean the skin a little bit if it's sweaty, but he will not be shivering. Okay, probably with the bath, he will have some shivers, he needs to be covered. If you expose him to put the leads, he will have the shivers, then you will have artifact in your ECG. Also, if you have devices like pneumatic compression, it causes some massage to the muscles, or some other devices, or bed, it having a massage. This makes vibrations that affect your ECG. So we spoke about machine, about patient, also my ECG machine. So what connects the machine to the patient are the wires and the leads and the modules. You have to inspect those modules are connected properly, and you connect the leads in the right electrode. Okay, so the electrodes, maybe you connect the leg leads and the chest leads. So then you will have ECG, but it will be wrong. Okay, so you have to connect the right leads to the right electrodes, and also make sure the leads are intact, they are not broken. For overuse, the covering of the leads can be exposed. The machine cannot know that, but it will show artifact. It will show the artifact. So you inspect the covering. If you saw anything that is broken, means any fluids, anything it is exposed to the environment, it will cause artifact in your leads. So let's say examples. If you have no baseline, means connection problem, probably. Connection problem. So check the leads are connected, make sure the machine is set up, make sure the connections, make continuity check. So what's the continuity check? You start from the patient until the machine. Everything is okay. From the electrodes, from the leads, from the modules, for the main cable, for the machine plugged in, the cable plugged in the machine. And check for proper cable. Maybe the cables, maybe it's not compatible with the machine. Someone fixed the wrong cables. And make sure the skin is dry. Now if I have another problem, baseline wonder. So what's baseline wonder? You see the ECG, but it's not going in a flat line. It's going up and down at this picture. So what is the meaning of this? What would be the possible reason? Patient is moving, okay? He is moving too much, or he is, you are not connecting the ground lead, which is right leg lead, okay? And you are using the same type of electrodes. You are not using the same type of electrodes. So your electrodes must be same manufacturer. So you open new package, you attach 3 leads, and you open new package with different manufacturer and attach it to the different positions. The machine will try to, it thinks the same reading coming from all these leads, same manufacturer, because the calibration, okay, for these leads, it will produce certain electricity rating, okay? The machine is adapt to this rating for one type. It will not measure, the machine will not know if you have 2 types. Okay, it cannot adjust. So it thinks it's one rating and they are different. So it will make this baseline wonder. So use one type. If you open new package, خلاص, remove the old one and apply new one. So you should be ready before. Do not apply unless you have the enough leads. You need how many leads? 10 leads. Okay, so you need to have 10 leads ready before. It's not attached already with the patient. With the same manufacturer. And next thing is the static. What is the static? Static build-up can be from other electrical devices, okay, or patient moving, or maybe the patient have a pacemaker beside him or something like that. This you cannot control, but other things you can control. Stop it, okay. Unplug other devices if it's not necessary, okay. Check for proper cables. AC noise, this is like also makes your ECG look bad. Doctor rejected, ask you for another version, sir. So what is the solution for that? Ground lead. First thing, think about ground lead. Ground lead is not connected, it will make noise in your ECG. Then you keep cables away from AC cords. Like let's say the ECG cables, if they are beside other AC electricity cords, it have magnetic field. Each cable have magnetic electricity, produce magnetic field around the cable. Probably the cable is not properly shielded, so it will cause the magnetic field to affect the ECG cable itself. So make the ECG cable isolated from other cables. Okay, not beside each other. Make other cables away from the ECG cable. And make the skin clean and prep the skin. Maybe the lights sometimes affect the ECG cable. I tell you, this is more appearing if your cables are degrading and exposed. So the lights can affect the ECG cable. Check dry skin. Make the patient, if he is moving, to stop moving. And also you need fully shielded cables. After all, you need fully shielded cable. Intermittent signal. So if you see the ECG, then it will be off. Then ECG off leads. So make sure connections are not loose. Okay. Dry the skin. Prepare the skin. Avoid static. You see, we came over repetitions, huh? Again, prepare the skin, prepare the machine, check everything, it will go okay. Really. Otherwise, the patient himself, he have shivers and you're not noticing. like maybe it's not strong shivers and very fine shivers, okay, you're not noticing it, but it's affecting your ECG. So try to warm the patient before doing the ECG, it will make the shiver go away. Okay, it can be, the shivers can be really strong, it's visible, maybe it's not visible. There is minor muscle contractions, it's not visible to your eye. So always rule out the cause of the shivers, which is fever and extreme cold. Okay, so these things need to be stopped. And also, if you have low amplitude, if you see the waves are very tiny, so probably your settings, there is something called gain. It will like having more sensitivity for the ECG waves. It's tapered down. So your sensitivity for ECG is less. So it sees the normal ECG as very tiny. So you adjust the machine setting, we will talk about that. And check the connection, check gain setting, we will, as I said, and other electronic devices can affect the amplitude. So now you prepare everything, connect the leads, prepare the machine. Okay, now you have the paper inside the machine. And not any paper can be used for the ECG. If you try to put A4, it will not print because the ink is in the paper. Okay, the machine just have the drawing pen and it's just producing heat, and this will burn the paper and it will show you this tracing. Okay, so this paper also is not, cannot use any paper because it has specific measurements, specific prints to allow you to measure and diagnose the ECG. So it has the measurements as a normal metric system using centimeters and millimeters. Okay, if you measure with a ruler, it will measure 5 millimeters for the large squares, and inside those large squares are small squares, each small square 1 millimeter each. 1 millimeter in the width and 1 millimeter in the height. Okay, so the width or the length in the paper, it represents how much time the ECG takes, how much the time the heart takes to produce the beat. Okay? Huh? For one beat? Yeah, this is normally for one cycle. We're talking about this is there is a range always, not only one number. Remember, anything in human anatomy, human physiology, there is range. So you are measuring from the P wave until the end of T wave, right? I think it's 0.8. So how much? Let's say up to how much? So we will learn individual waves, and this is good start that you know already from previous lecture. But I'm talking about the paper now, okay, itself. Okay, if you have abnormality or normal, so how you will differentiate from the paper? You count the paper itself. It's like a ruler, and you draw on the ruler itself. So already the paper have the ruler. Before you don't have the print out, so you bring the ruler and you measure the waves with the ruler. But now the paper have the ruler, so it will just, it's a matter of that you are counting how many squares, large or small. So first of all, we have to learn the standard for the measurement. Here, you have 5 by 5 for each large square, right? Large square. The paper consists of large squares and small squares, and the large square 5 by 5, equal in height to width. So in the width, each large square equal to 0.2 seconds. So, well, how is that equaling time? The machine print out the paper in a certain speed. Okay, in a certain speed. So if I will tell you like the machine will print hold this paper in 10 seconds. In 10 seconds. And the paper length is 10 centimeters. So how many centimeter per second? 1. Okay, just rough idea. This machine print out 25 millimeter or 2.5 centimeter per second. Okay? Bear with me. Remember this number. Each second the machine print out, the paper come out of the machine with a speed equal to 2.5 centimeters. So means if you run the machine for 1 second and stop it, you will see the paper out of the machine measuring only 2.5 centimeter or 25 millimeter. Okay? If you leave it for 2 seconds, it will be 25 and 25. So 50. Okay, if you leave it for 3 seconds, 25 and 25 and 25, 75. If you leave it for 4 seconds, 25, 25, 25, 25, and etc. So you get the idea? You get the idea? So how much you allow the machine to print the paper, it will produce this much per second, okay? Per second. So 25 millimeter per second. Remember, this is the standard speed. You can make different speed in your machine. You can make the setting different. You can make it, let's say, 50 millimeter per second. So it go faster. It will go out of the machine faster. So instead of 1 second 25, no, 1 second 50. So it will take out of the machine faster. Right. This is the horizontal plane. So the paper will go out this way. What about the vertical plane? So the vertical plane also same, 1 millimeter, small square, large square, 5 millimeter. It will affect my amplitude. So always when you see the waves, some waves are taller than other waves. So that is short and the other waves are tall. Okay? To measure this height, okay, we are measuring them in millimeter, and this gives us how much energy produced in this wave. Let's say you have the P wave. Why the P wave is small? Because it's produced in the atrium. Okay, produced by the atrial muscle. Why the QRS is large? Because it's produced by the ventricle, and ventricle is stronger. So the stronger ventricle makes stronger contraction, makes stronger electricity. Stronger electricity. How can I measure this electricity? By how much high the wave. So the wave will reach high level if it is strong energy. So they call it amplitude. Amplitude. Okay? So we are measuring the amplitude in the height, and then we're measuring the time. So we are measuring time and amplitude. Okay? Just remember this, as this is basic knowledge. This is basic knowledge before we move forward. And this is the standard speed. Time, each second it takes 5 large grids, and each grid have equal to 0.2 seconds. Okay, so in 1 second I have 25 millimeter. Okay, 25 millimeter or 5 large squares. So how many for 1 second, right? How many seconds in 1 large square? I have 1 second, 5 large square. I want to see how much time in 1 large square only. 0.2. Huh? 0.2. Now try to divide 1 by 25. 1 by 5, sorry. 1 by 5. 0.2. Just I need everyone try your calculator. Take out your phone. Divide 1 by 5. How much is this produced? 0.2. Okay? Because I said 5 large square in 1 second. So how much seconds in 1 large square? 0.2. Okay? You get it now? Type. I'm talking smaller now. I will talk smaller. The small square. How many small square in 1 second? 25. So now divide 1 second on 25 small square. How much time in the small square? 1 divided by 25. Huh? Anybody got a different number? Anybody got a different number? All got the same number? Huh? Yeah. So 0.04 is a small square. Okay? 0.04 is a small square. Why is it important? Because my ECG waves are small. Okay, so this wave takes 3 small squares. So 0.04 plus 0.04 plus 0.04. So you measure the length of the waves, or how much time the wave takes in these small squares. Okay. So usually the paper are marked every 3 seconds or every 15 large squares, right? Because how many large square in 3 seconds? It said 1 second 5. So 3 seconds, how many large square? 15. Okay, how many large square in 6 seconds? How many? Yalla, tell us guys. Tell us. Now I have 1 second, 5 large square. So how many large square in 6 seconds? Huh? Anybody? Huh? 30. Okay. How many large square in 12 seconds? Use your calculator, use your phone, it's okay. 60 large square. Okay. Just to get the idea. Okay. So every second 5. So multiply that by how many seconds? Then you will have that. How many large square in 60 seconds? How many large square in 60 seconds? 60 seconds. 60. Each second 5. Now multiply by 60. Each second large squares 5. Yalla, use your phone. Now you have each second. You have each second 5 large square. Now make this paper print out for 1 minute, 60 seconds, right? This 1 minute is 60 seconds, right? So print it out for 1 minute. So how many large square? 300, okay? So how many large square per minute? 300, because the minute have 60 seconds and every second is 5 large square, okay? So now we talk about small square now. How many small square in 60 seconds? Now I have 1 second, how many small square? How many? 1 second, how many small square? 25. Each second 25. Now I have multiplied 25 by 60. 25 by 60. How much? 1,500. So each minute, the papers, if you turn on the machine and let it run for 1 minute, then stop, it will print out 60 seconds of time equal to 300 large square or 1,500 small square. Okay? 1,500 small square. Okay? Okay, guys, remember these numbers. Okay? So we talk about time now. Okay? What time? What's good? Okay, we are talking about time now. Now this is the horizontal plane. Okay, we didn't talk about the vertical plane. Not yet, okay? Now let's talk about the vertical plane. So the vertical plane, each small square equal to 0.1 millivolt equal to 1/10 of a millivolt. Okay, so how many small squares in the 1 millivolt? Now we have the small square. I'm talking about the height now. It will show the wave, it will be high or amplitude or low amplitude. Okay, it will be tall or short. So the wave reach until here, or the wave can reach up. Okay, higher. So each small square means equal to energy 0.1. 0.1. Okay? You get it? Now, so 1 small square equals 0.1. How many small square equal to 1?
10.
Now, try others. Anybody have a different number? Guys in the back, how much? Anybody here in this side? Guys, you got the answer? How many small square in 1 millivolt? You know how to do it? Huh? How much?
0.1 multiplied by 10 is equals to 1.
Yes, because you divide 1 over 0.1, it's 10. Okay? So this is the 10 small squares equal 1 millivolt. So 5 small square equal to how much? 5 small square equal to 0.5 millivolt. You get it? Let's say I don't have a marker here. You're not using marker, right? Guys, just معلش. Listen. Over here. This is 0.1. This is 0.1. This is 0.1. 0.1 plus 0.1. How much? Are you sure? Anybody have different answer? 0.1 plus 0.1. Huh? 0.2, sir? So 0.1 plus 0.1, 0.2. Then another 0.1, 0.3. 0.4, 0.5, okay, another one, 6, 0.7, 0.8, 0.9. What's after 0.9? 0.9? 1. If it is 10, the 0 will be in this side and the 1 will go to the other side. Okay, this is point means the fractions. Okay, now you have whole 1. Okay, you have whole 1. Okay, you get it, guys? So you need 1, 2, 3, 4, 5, 6, 7, 10 small square to have 1 millivolt, okay? Anybody don't get it now? Okay. Right. So why you need it? Because usually when you have ST segment elevation, if you heard about patient have STEMI, patient have MI, have diagnose how much elevated the ST segment. So ST segment, it will be supposed to be here 0. Now it is here. So how many small squares? 4. So 0.4 millivolt elevation of ST segment. So that's why when you diagnose it, it should say above 0.1. Okay, 0.1 or more. Some books said 0.2 or more. 0.2 what? 0.2 millivolt. 0.2 millivolt. Okay. So this is a standard setting. You put your machine on this setting. See the speed, the setting name is the speed, print speed, and the gain. See your ECG machine. Play with it. Open the setting. You will find something called speed, the other one is called gain. Okay? Speed and gain. The speed has to be 25 millimeter per second. And the gain has to be 10 millimeter per millivolt. Okay, guys? Anybody have any doubt? Should we clear it now? Later, other than we will have more confusion later. Okay? Shall I move? Right. So now We will some ECG waves are up, some ECG waves are down. What's the difference? There is one line in between. Okay? This line is called the isoelectric line. This is the no energy. This is the balance. In between. This is between the high and the low. This is the zero. No energy here. Isoelectric line. No energy. The flat. If the patient have cardiac arrest, he will have only this line. Okay? If the heart start to work, it will go up. It will go up. Okay? Or down. So, what is above this line? Positive. Below this line, negative. Negative what? Deflection. Okay? It deflect above the line, positive. Deflect below the line, negative. Please remember this. Okay? We will talk about positive deflection, negative deflection. Then you will remember, yeah, what's above the line is positive. Below the line is negative. Anybody have doubts? Shall I move? Okay? It's very important for me to make everyone 100%. This is basic. Okay? If you don't have the basics, you will get confused easily when you speak about ECG. What is this? It's like chemistry. Okay? So let's talk about other terminology. Wave, any deflection. Any deflection. So flat line, no deflection, no waves. Anything above the line. So that's why I explained already. Segment, any flat part of the isoelectric line. Flat part. This is a segment. PR segment, ST segment. Okay, flat line, not wave. Not a wave. Another thing is the interval. Interval include two parts of the ECG or more. Wave and segment. Can be one wave and one segment. Can be two wave, one segment. So this is any, we say interval, include a wave and a segment, at least. Okay? So this is three terminology you learn now. Now, interval. Okay? Then, normal ECG tracing consists of these waves. P, Q, R, S, T. Okay? I have no idea why they start from P. Why didn't start from A? I have no idea. Don't ask this question. Okay? So, they start from P, then the Q, R, S, T. So easy to remember, huh? P, Q, R, S, T. Okay? Maybe they reserve the other letters for other abbreviations. So, the P waves is the beginning. So the start of the cardiac cycle, as explained by Mr. Eric, first the atrium will contract. Okay? Then the ventricle. What makes the atrial contract? The sinus. SNO. Okay? Then you will have the P wave, and you know the depolarization and polarization already explained by Mr. Eric. Any further explanation needed? Guys, you know what is the waves force, huh? So, QRS complex, the ventricular depolarization. Okay? And the ST segment, okay? Flat. Isoelectric line at the end of the S and the beginning of the T wave. But you have to know something called the J point. So the J point is, let's say, the S wave will start to go up. It's going down. Okay, you have the Q wave, positive or negative deflection? Negative. Then the R wave, positive. Then the S wave, negative. Okay? Then it will go back to isoelectric line. Now, this is perfect ECG, huh? It will never come like this. It will maybe you have a noise, you have something. So when should I say there is ST segment elevation? You see, it's the line is going up. Once it start to have an angle, okay, divert, this is the J point. From there, how much high this point from the isoelectric line, this is your ST segment elevation. Okay, because the ST segment is not flat, maybe oblique, maybe curved, okay, maybe skewed. So you need to identify this point, and this is a point of elevation for ST segment. Then the T wave. So the QT interval, this one of the intervals here, from the beginning of the QRS till the end of the T wave. Okay? And there is some rarely appearing